Hi, welcome to Chemistry Unit 3 on chemical bonds. Today we're going to start 3.1. This will be 3.1a. And we're going to talk about valence electrons, dot diagrams, oxidation numbers, types of bonds. And then next time we'll be talking about polyatomics and the transition elements. So let's get started. Remember your valence electrons. Those are the number of electrons in the outer energy level. Those are the ones involved in bonding. They're associated with that group number, and these should already be on your periodic table. Dot diagrams, remember, are used to show the valence electrons with the symbol. Okay, and we're actually going to use dot diagrams to show how elements bond together. Oxidation numbers. Oxidation numbers are a new thing, so you may want to pause and write this down. Oxidation numbers are the number of electrons that an element would like to gain or lose to complete its outer valence shell. Absolutely all atoms and compounds want to have a complete outer shell. 8 electrons, called an octet, completes any outer shell. And these oxidation numbers come from the valence electrons because it's what they want in order to make a complete shell. So on your periodic table, you already have the group numbers 1 through 18. Above those, you have the valence numbers, and those are circled. Group 1 was 1, 2 was 2, groups 3 through 12 had no valence, so on and so forth. And then above that, on the periodic table, you need to write group 1 valence as a 1 positive oxidation. Group 2, valence of 2 is a 2 positive oxidation. Then groups 3 through 12, you're going to write just positive oxidation. We'll explain those a little later. Group 13 has a valence of 3. That's a 3 positive oxidation. 4 is 4 plus or minus. Valence of 5 is a 3 negative. 6 is a 2 negative. 7 is a 1 negative. And 8 is 0. Okay, so oxidation numbers come from the valence electrons. It's what they want. A valence of 1 through 3, they want to lose their electrons to become stable. That's why they're positive, because they make themselves into positive ions because they lose their electrons. A valence of 5 through 7, they want to gain electrons in order to be stable. That's why they're negative, because remember, electrons are negative. They want to gain more negative things. But a valence of 4 can go either way, okay? Because it can either be positive or negative, and we try not to play with those very much. So if you looked at your periodic table, hydrogen, lithium, sodium, they all have an oxidation number of 1 positive. Because they all have a valence of 1, they would like to give 1 electron away in order to be stable. While at the same time, fluorine, chlorine, and bromine have oxidation numbers of 1 negative because they would like to get 1 electron to be stable. Okay, so you have 2 types of bonds. Ionic bonds, where the electrons are lost and gained between atoms. These occur between metals and nonmetals. These will use the oxidation number. The second kind is covalent. Covalent are where the electrons are shared between the atoms. They will occur between 2 nonmetals, and you will be given the number of each element to use. Okay, there's not a question here, and you don't have to figure this out. For bonding purposes, you wrote a stair step on your periodic table. For bonding, all of the elements to the right of that stair step, in that upper right-hand corner, those are all considered non-metal for bonding. While at the same time, everything to the left of the stair step is considered to be a metal. Remember that hydrogen is the weird one. It can do whatever it wants to do. Okay, so you have you have two types of bonds, but within ionic, you have 4 different subtypes, if you will. You have perfect, where the oxidations cancel out and there are no subscripts. You have crisscross, where the oxidations will crisscross to become subscripts. And then you'll have polyatomic and transition. We'll talk more about those in the next video. You also have covalent. So these are examples of perfect ionic compounds. Sodium and chlorine, they both have an oxidation of 1 positive and 1 negative. They'll make the compound NaCl. Potassium and bromine, same thing, will make KBr. Magnesium and oxygen will make MgO. And calcium and sulfur will make CaS. Remember, capital lowercase is very important. So, what happens if they're not perfect? Well, this is the crisscross method. If you had hydrogen and oxygen, hydrogen has an oxidation of 1 positive, oxygen is 2 negative. They will literally crisscross. The 2 comes down from oxygen to hydrogen. The 1 comes down from hydrogen to oxygen, and you're left with H2O. That means 2 hydrogen would combine with 1 oxygen. Again, calcium and chlorine. Calcium is a 2 positive oxidation. Chlorine is a 1 negative. The 2 would travel down. The 1 would travel down. And you end up with CaCl2. 1 calcium combines with 2 chlorine. Things to notice about ionic bonds. 1, the final answer. If the subscripts match, we leave them off. If we keep those subscripts, like Mg2O2, that makes a molecular formula. While if we remove them, MgO, that makes an empirical formula. The positive oxidation always comes first, and you do have to pay very close attention to that capital lowercase and the placement of subscripts. Covalent bonds share their electrons, and you have to be given the number of each element. So 1 carbon and 1 oxygen becomes CO. 1 carbon and 2 oxygen becomes CO2. 1 phosphorus and 3 chlorine becomes PCl3. The number is its own subscript. There's no movement. It just is what it is. So your assignment today is going to deal with ionic either being perfect or crisscross and covalent. We'll do lots of assignments and demonstrations in class. Thanks for watching.